Hi, I'm Nathan, and today I'm going to be taking you through a tutorial on how to simulate cavity flow in a box. So this video is slightly longer than the previous videos I've made, and that is because this is a complete tutorial. I'm going to be taking you from the start to the finish of how to run a simulation. So I'm starting here with how to do the CAD. I'm just doing a very simple box on CAD. The CAD software I'm using is called NX12. As you can see here, the dimensions are 1000 by 1000, and this is just because this is in millimeters, and I would like it to be 1 by 1 in STAR CCM. NX defaults to millimeters, while STAR CCM defaults to meters, hence why I've got it as 1000 here. So first thing you're going to want to do is load up STAR CCM. Just name it something you're going to remember. So the first step here is we're importing the CAD that we've just generated on NX into STAR CCM. First, we want to create a new geometry part just from this CAD that we've imported. And to be able to see this, we've got to create a scene. So here we create a geometry scene. As you can see, this is the part we've just drawn on NX. So next, we're going to want to split the surface into parts by part curves. So as you can see here, each surface of this cube is different. I'm just going to name them left, right, front, back. So then you're going to want to assign parts to regions. You want to create a boundary for each surface part. So that's just to say that the left, front, right, back, top and bottom each have a different boundary. This is helpful because we want to impose different conditions on different boundaries. So this is just me selecting the physics here. To be honest with you, the reason I'm choosing a smaller value for the viscosity here is so that the simulation converges faster, just so that you don't have to wait as long while I run it. So here I'm setting the top to a velocity inlet. The rest of the surfaces are walls, meaning it's imposing 0 velocity. And we're going to choose it as a 1 velocity in the X direction, meaning the velocity on this top surface is just going left to right. And then it's going to induce a flow field in the rest of the cube. So this derived part is just for the visualization when we run our simulation. So I'm going to create an automated mesh, tetrahedral mesh. This is just the simplest mesh to generate. And I'd also like a prism layer to better capture the boundary layer. So as you can see here, I'm just changing a few of the settings here just to make a slightly better mesh. You can play with this to create better meshes, and if I made the base size smaller here, then we would have a finer mesh which would more accurately capture what's going on, but it would take much longer to simulate. So in this simulation, I'm doing a pretty coarse mesh just so that it converges within a reasonable amount of time for this video. add like 3 layers in 3 prismatic layers. Execute the mesh. The mesh is generated. Now to see it, we again need a mesh scene, so a new scene mesh. Here you can see the mesh, looks decent, tetrahedral mesh. Be good enough to run a simulation. So I've initialized and then run, and you can see straight away the residuals are converging. You like to see the velocity vectors, so here we're doing a new vector scene, which is just these velocity vectors, and we have to select which parts we'd like to see it on. First I'm going to select this derived part, which is this mid-plane. As you can see, we have velocities going left to right in the top, and then it's creating some circulation. So thank you for watching this video. I hope it's been helpful. Let me know any questions you have or any videos you'd like to see in the future.